Hello. In this episode we will see how the image data will be displayed on the screen. An LCD screen needs several electronic circuits to drive the display and control the set of pixels. These circuits are grouped in chips called LDI, which is the acronym for LCD Driving IC. We saw in a previous video one of these chips placed on the side of the screen called gate driver. This component controls in a horizontal way the supply of the TFT via their gate with VGH and VGL. For the image data, they are transmitted vertically to the source of TFT. The chips that control the data are located at the top or bottom of the screen. These chips have several names like source drivers in reference to their connection to the sources of the TFT, data driver or column driver because of the vertical arrangement of this control resembling columns. In this illustration we can see the layout and organization of the different drivers that control the TFT. Here, we will focus on the source driver. As its name indicates, this chip is connected to the TFT sources. For its correct operation, it must receive from the TCON board the gamma voltages and the data. To complete the electrical loop at the TFT level, all the drains and the storage capacities are connected together at the same voltage, which serves as a reference value. This reference voltage comes from the TCON board and is noted VCOM or sometimes VCM, which is an abbreviation of common voltage. The common electrode, whose position can be seen between the different layers of the screen, is nothing more than the sum of all the conductors connecting the drains and the storage capacities ending at the same place. A particularity to know is the way the wiring of the storage capacitor is done. There is the technique seen previously called cap-on common structure, and which consists in connecting to the same VCOM circuit, the liquid crystal and the storage capacitor noted CS on this figure. The second method called cap-on gate structure connects the storage capacitor to a line of the gate driver. This technique is not suitable for screens larger than 20-inch because it increases the capacitive load on the gate driver. On the other hand, for the first technique, it is reproached to decreases the opening which allows the passage of the light towards the subpixel. This concept of passage of light through the various structures to illuminate the subpixel is called aperture ratio. On this figure, we see on the cut the superposition of various elements of the screen, some of which are opaque to light as the electrodes of TFT and storage capacitors, the vertical lines of the data and the material of the black matrix. The aperture ratio of the pixel, represented here by the red arrow, is calculated by dividing the surface of the opening of the pixel divided by the total surface of the pixel, represented here by the black arrow, and which includes the pixel and the opaque elements. To understand the role of the different gamma voltages that will go to the driver source chip, we need to go back to some notions seen in previous episodes concerning the properties of the liquid crystal. The latter is assimilated to a non-polarized capacitor because in its architecture we find all the ingredients of a capacitor with a double conductive armature made here from a transparent conductive material called ITO. These two armatures are separated by a double insulating layer based on polyimide and between which the liquid crystal is trapped. As this liquid crystal capacitor does not hold the charge properly, a real capacitor has been added in parallel to hold the charge until the voltage change on the liquid crystal capacitor. The liquid crystal is used because it has optoelectric properties which allows it to modify the orientation of these crystals when it is subjected to an electric field. Depending on the electrical voltage applied to the liquid crystal armatures, the intensity of the light that passes through it will be variable. The combination of the three RGB lights with variable intensity values allows to obtain millions of different shades of colors. It is this property which is used in the LCD screens to obtain the colors. Another element to take into account to preserve this electrical property is to avoid to apply a voltage with the same polarity to the liquid crystal over a long period. Doing so may freeze the liquid crystal and make it unable to change its orientation regardless of the electric field applied to it. To preserve this ability to change the orientation of the liquid crystal according to the voltage applied to it, the polarity applied to the electrodes is reversed. With the same voltage and reversed polarity, the same amount of light passes through the liquid crystal. The only difference is the direction of movement of the liquid crystal, which is different and does not impact the number of photons that cross the liquid crystal. Here is an animation that shows various ways to control the polarity of the pixels. With a double command of gate driver we can reverse the polarity of the pixels located on the same column. Another way is to change the polarity of each subpixel using a single gate driver command and connecting the subpixels in this way. At the end of the frame you get a different polarity between each pixel. It should be noted that it is not the gate driver that changes the polarity of the subpixel. It is the value of the voltage applied to the TFT source that will determine the direction of polarization of the liquid crystal. This concept will be developed in a moment with the introduction of the role of gamma voltages in the reference voltage Vcom. Among other techniques to control the polarity of the pixels, there is the method of inversion of the frame. On a frame all pixels have the same positive or negative polarity. In the next frame the pixels will have a polarity opposite to the previous one. Another method of changing polarity is the inversion of the polarity between two lines. On the TCON board, the signal that allows the control of the polarity of the pixels is often written under the abbreviation POL, as seen on this board. We will now see what the source driver chip is made of. Here is its block diagram. There are the following circuits: a shift register, latch, a digital to analog converter noted under its acronym DAC, and a voltage follower or buffer. We will start by giving some details on the first two components, namely the shift register and the latch. Shift registers and latch registers are built from flip-flops. They are electronic circuits belonging to the sequential logic. In the latter, the output operation depends on the state of the primary inputs and the states preceding the output, called secondary inputs. This is to be differentiated from combinatorial logic, where the output depends at a given moment only on the state of the inputs. With the sequential logic, it is possible to keep and store the information. In combinatorial logic, this is not possible. On the electronic level, combinatorial logic is made from transistors grouped together to create various logic gates such as NOT, NOR and NAND gates. In sequential logic, electronic circuits are made according to a particular arrangement of various logic gates. As we have just said, in sequential logic, the basic device used is the flip-flop. These are bistable elements that can take the state 0 or 1, and they can keep it, hence their use as a memory circuit. In the flip-flop, we note on the symbolic representation an additional input in the presence of a triangle. This symbolizes the input of the clock signal which is necessary for the operation of the flip-flop. In a classic latch there is no clock. The clock signal can be used in several ways. Either when the signal goes from the low level to the high level. This is called the rising edge of the clock, or the opposite. The control of the flip-flop is done when the clock signal goes from the high level to the low level or falling edge of the clock. This technique is called edge-triggered flip-flop. If in a circuit the clock signal is used when it is at its high or low level, this technique is called level-triggered flip-flop. The control by the high level of the clock is called the positive level triggered. The control by the low level of the clock is called the negative level triggered. Sequential circuits that operate in the presence of a clock are said to be synchronous because the output depends on a synchronization signal from the clock. The sequential circuit is called asynchronous when the output does not depend on a clock signal and only depends on the state of the input variables. The latches named SR are called so in reference to the two inputs labeled S for set to 1 and R for reset to 0. The outputs are labeled Q and its inverse Q bar. On the symbol of the latch SR, the inverted output is materialized by a circle placed in front of this output. On the circuit diagram, we see two types of latch according to the logic gates that constitute it. There are latch SR NAND and latch SR NOR. The latch SR is called gated or clocked SR latch when a control by an enabling signal is added to it. The circuit is constructed by adding another logic gate after the SR latch and a third input corresponding to the enable signal. The D flip-flop is obtained by keeping only one input named D for data. In electronic terms, the modification made to the previous clocked SR latch is the addition of a connection between the set and reset with a NOT gate. The D flip-flop is an edge-triggered flip-flop. It works with the rising or falling edge of the clock. If the D flip-flop is a positive edge triggered, the output Q will take the state of the D input on the rising edge of the clock. Thus, if the input equals 0, on the rising edge the output Q will be equals 0, and if the input equals 1, on the rising edge the output Q will be equals 1. The latch is a variant of the previous D flip-flop. It is a flip-flop without a clock edge detector circuit. The term clock is replaced here by the word enable because this flip-flop is of the level trigger-end type, i.e. it only works with a high clock state, if it is of the positive level triggered type, or negative level triggered, if it is calibrated to work with the low clock state. We have seen that the flip-flop has a memory function with a single bit value of 0 or 1. By putting several D flip-flops in series, we create another type of circuit called a register. The number of bits that a register can contain will be equal to the number of flip-flops that constitute it. The data stored in it can be written or read in different ways, either all at once or one after the other. According to the mode of operation, we distinguish 4 types of registers which are noted under their English acronym thus: SIPO, serial in parallel out; SISO, serial in serial out; PIPO, parallel in parallel out; PISO, parallel in serial out. For the SISO, serial in serial out register, the data enters and exits in series. For the SIPO, serial in parallel out register, the data enters in series and exits both in parallel and in series. In PIPO, parallel in parallel out register, the inputs enter in parallel and exit in parallel. This is the principle on which the latch works. In PISO, parallel in serial out register, some logic gates are wired to the flip-flops according to this diagram. There are 2 steps in the operation of this register. The first step is to load the register with the load signal, and then comes the step of outputting the data from the registers in series with the shift signal. In this example, we see the arrangement between a shift register composed of 8 D flip-flops configured in SIPO, i.e. serial in, parallel out, which allows 8 bits or 1 byte to be stored, followed by a latch also composed of 8 D flip-flops configured according to a PIPO, parallel input, parallel output. The shift register works with a clock signal according to the edge-triggered mode, while the latch clock operates with the level-triggered mode. For the shift register, it would take 8 clock pulses to enter the 8 bits of data in each of the flip-flops. On the other hand, a single clock signal is enough to obtain the data output from the latch. At the shift register we find the STH signal, which is an abbreviation of horizontal start. It is the signal of the beginning of horizontal scanning. The shift register is often of bidirectional type. This allows the data to be read in both directions. To specify the direction of the data reading, the letter R of the word right, or L of left is added to STH, which gives STHR, for a reading of the data from the right to the left, and STHL, in the opposite direction. For information, we can find on the datasheet instead of STH, the label SSP, which is an abbreviation of start source pulse. It is the same signal of beginning of horizontal scanning. CPH is the shift register clock signal. CPH is an abbreviation of clock pulse horizontal. For the latch, the signal has various names. We can find enable, load, or TP. TP is an abbreviation of totem pole in reference to an electronic circuit built like a push-pull circuit but with a resistor, and 2 transistors of the same type, between which there is a diode. In the example presented here, the totem pole output is part of a NAND gate circuit built on the basis of a bipolar transistor. The previous configuration can be represented by this diagram. The different circuits allowing to control the shift register and the latch are grouped in a circuit called logic control. Compared to the previous figure, there may be additional control circuits like a reset for the shift register and an output enable control placed after the latch clock. Here is an example of the inscription on a TCON board of the various clock signals intended for the shift register and the latch of the source driver. On this board, we find the inscription STH for start horizontal. STHR gives the precision of the data reading direction, here shift right, which means reading the data with a shift to the right. For the term TP, it should not be confused with the abbreviation often used to designate the test point of an electronic board, which allows to make measurements of voltages or signal at different places according to the manufacturer's specification. In the case of the source driver, the term TP, which comes from the abbreviation of the words totem pole, designates the latch signal. A number can accompany the TP of the test points when they are numerous. In the same way, when there are several source drivers, one can find a number or a letter accompanying the TP inscription of totem pole to locate them compared to each chip of source driver. On this TCON board with 2 connectors on the panel, a letter A or B has been put in front of STH to differentiate them according to their direction on the connectors. Same thing for TP, to which the number 1 has been added. Now we are going to see the DAC placed after the latch and before the buffer. What is it used for? As we said before, DAC is the acronym of Digital Analog Converter. It is an electronic circuit which allows to convert digital data into analog data. We will take the example of the display on the screen of the color plum, coded on 8 bits. We see on this image the decimal values of the 3 subpixels RGB and their numerical correspondence. It is the mixture of these 3 colors, with the values indicated, which will give the pixel the color plum. To display this plum color on a LCD screen, it is necessary to apply on the source of the 3 TFT transistors composing a pixel, the 3 values corresponding to the level of gray of each color red, green and blue. We see at once that there is a problem in this circuit due to the fact that the TFT transistor works only with an analogical tension while the data of the image is in digital format. To solve this problem, we use a circuit that converts a digital value into an analog voltage. To do this conversion operation, the DAC needs the gamma voltages and its correction factor. The exact role of gamma and its production by the TCON board has been explained in previous videos. Here we will see instead how the different gamma voltage values will be used to obtain analog voltages with a gamma correction. The gamma voltages are divided into 2 groups. Those above the VCOM have a positive value and those below the VCOM have a negative value relative to the VCOM. The purpose of having positive and negative values is to vary the polarity of the pixels to preserve the optoelectrical characteristics of the liquid crystal. Here is an example that shows how we can obtain the same data value with 2 different voltage values. The V-gamma4 is above the VCOM. Its value is positive. The V-gamma7 is below the VCOM. Its value is negative. The value of the data in decimal 192 can be translated into an analog value in the form of a positive voltage V-gamma4 or negative V-gamma7. The liquid crystals will be oriented for this value of data according to the same angle but with a different direction. This will not affect the amount of light that will pass through the liquid crystal. It is with this technique that we can change the polarity of the pixels. The DAC is connected to the gamma in this way. It uses a voltage divider bridge made of a series of resistors. The gamma voltages are intercalated between a determined number of resistors. For the illustration, we will use 3 resistors and 3 gamma values for the positive references and 3 gamma values for the negative references. From this assembly, we can see that we can obtain different values of analog voltages. 7 positive values from V1 to V7 and 7 negative values from V8 to V14. If the data uses an 8-bit encoding, this will give values ranging from 0 to 255, i.e. a total of 256 gray level values. For each value of the data, it will be necessary to make it correspond to an analog voltage. For example, with 5 positive and 5 negative gamma values, it will be necessary to put a series of 64 resistors between each gamma reference to obtain 256 positive and 256 negative analog voltages. If the number of gamma values is higher, for example 18 gamma values, the number of resistors in series to be placed between each reference will be less important. With this assembly, we see that we make correspond to each value of the data a value of voltage either positive or negative if it is below the VCOM. On this figure is represented on the first column in blue, the value in decimal of the data coded on 8 bits going from 0 to 255. On the second column is written the binary correspondence to the data. In the column colored red, we find the value of the positive voltage at the output of the DAC and its correspondence with the data. The column colored in yellow lists the negative voltage generated by the DAC. So for the same binary number, there are 2 voltage values that can be applied alternatively to the TFT source to obtain the same amount of photon that will cross the liquid crystal but with a changing polarity which will preserve the functionality of the subpixels. In the previous example, to display the plum color, the digital value of the 3 colors is replaced by the DAC with 3 respective values in analog voltage. The use of the positive or negative value corresponding to the nuance of the 3 RGB colors will not affect the nuance of the final color that will be output. We return to the block diagram. We understand better the position of the DAC in relation to the shift register and the latch. At the input of the DAC, the 8 digital values coming from the latch are transformed into a single analog output. The DAC receives the POL signal, i.e. the signal which allows the control of the polarity of the subpixels. In the block diagram, after the DAC, there is a buffer or voltage follower circuit. The purpose of this buffer is to separate the source driver circuits from the influence of the TFT transistors and storage capacities inside the panel, which constitute the load to be supplied with voltage. Here is an overview with a block diagram with the various signals. At the buffer level, there are two additional signals SOE and STB. SOE is an abbreviation of Source Output Enable. This signal is used to control the output of the analog voltages of the buffer. For the term STB, you have to refer to the datasheet to know its real function. STB can be used as an on-off switch on the DAC and on the buffer. In this function, STB is an abbreviation of standby. An example of setting this pin, at high status, STB is in on mode. At low status, STB is in off mode, i.e. the DAC and the buffer are stopped. In the datasheets of the source drivers, additional circuits such as a level shifter can be found, but the general principle of operation remains unchanged. Here STB is used as a clock signal acting on several levels with various functions. On the rising edge of this clock, STB has a reset function on the shift register and at the same time a data transfer function from the data register to the latch. On the falling edge of STB, the analog voltage generated by the DAC is transmitted to the buffer. In addition to the various signals we have seen, the source driver receives a power supply noted VDD, VSS for the digital voltages, VCC and GND for the analog voltages. The latter can be noted VDDA and AGND. The letter A added comes from the word analog. For the digital ground, there is the notation DGND, D coming from the word digital. On this TCON board, next to the polarity control signal labeled POL, there is the inscription SOE, which is the abbreviation for Source Output Enable. There is the inscription VDD for the digital voltage. For information, the inscription GSP is the abbreviation of Gate Scanning Start Pulse, which is nothing else than STV or VST. On this other board, next to POL the polarity signal, we find the STB inscription. DO is the abbreviation of Data Input Output. VEE is VGL and VGG is VGH. This short animation illustrates the process of transferring an 8-bit data to illuminate the subpixels. The data is transferred from the shift register to the latch. At the DAC level, there is a pin called POL which allows the adjustment of the polarity. An example of the setting of this pin, in the high status, the positive voltage values are selected and in the low status the negative ones. This animation summarizes the process of generating the different colors, by combining the three primary colors red, green and blue. This process will be repeated for each pixel that contains the screen, until the complete display of the image. We arrive at the end of the video. Goodbye and see you soon.